Let me first do the, is it recording now? Yes. Okay, so you can see my screen now?
Yes, sir.
Yeah. Okay, so just a quick recap. We have already talked about the application. Yes. Hello. Okay, all right. So before I move ahead, so we have already talked about the ethos formula and its application to derive the Black-Scholes result. And we have done some simple applications, but now is the time to go back to the number of examples that we discussed and look at them again and see how the Black-Scholes result can be modified to extend to those more complicated derivative contracts. So there are some exercises in the book. So I gave you some of them. I will list some others. So you have to now start working on them. So whenever you have a contract, derivative contract, you have to find a price. And in continuous time, the ethos formula is usually the toolbox that you have. Of course, unless it's a very simple option, it will not be as neat as the Black-Scholes formula for the European call option. It will be more complicated, but the basic principle will remain the same, that you will always try to set up a riskless portfolio, at least for an infinitesimal amount of time, and then using the no arbitrage principle, equate the return to the bank rate and derive the excuse me, derive the corresponding differential equation, actually a partial differential equation. For simple cases, we will get standard PDEs and solutions are known, so you can actually derive them explicitly. But beyond that, typically explicit solutions will not be available. We can set up the PDE, but then we have to take recourse to numerical methods to get a solution. That's usually how it goes. So today what I will do is I will do something simple. I will basically try to show how a stochastic differential equation can be explicitly solved. Of course, there is a related question to that. There are two questions here. One question is actually how do we know that solutions exist, and even better, it's unique. For a standard differential equation situation, without the stochastic part, we know that there are standard theorems like the initial value problem and other conditions, Lipschitz criterion type conditions, which guarantee that a solution will exist and the solution will be unique. Similar questions arise here also for the stochastic differential equation, and we will tackle them, but we will tackle them later. First, we will do the easy thing. Well, not easy, but at least theoretically less demanding. We will first try to look at how these equations are solved. So what is the mechanical part of it? Solving differential equations for some standard canonical cases. Because beyond that, again, as you all know, that differential equations are notoriously difficult to solve analytically. So we will do the canonical standard cases, things that you have already seen before in the non-stochastic context. So we will start with the population growth model. That was the first example that we took, and that is the first one that we will try to solve explicitly. So our initial formulation was like dNt by nt equal to some AT, where the AT is the growth rate, the time zero population size is given. We normally take it as a constant, but you can also take it as a random variable whose distribution is known. That won't make a difference to the solution technique. AT is the growth rate, and here our point of departure is that AT is not deterministic. So we think of AT as consisting of two parts. One part is the deterministic growth rate, RT, but there is also a white noise part. So the two parts together typically constitute our population growth model. In general, we are going to look at explicit solution methods for SDEs of this type, dxt equal to bdt plus sigma dB. That's our typical Ito process formulation. And as I said, that Ito process formulation gives us a lot of power because we already know from Ito's lemma that this is closed under smooth maps. And in fact, we know something more. We now know that because of the Martingale representation theorem, if I can show that a process, a price process is a Martingale, then we definitely have a Ito representation for it through the Martingale representation theorem. So it is like if and only if. So all the cases that we are really interested in can be converted to the Ito process. Okay, is that clear?
Yes, sir.
So basically I'm trying to zoom in onto the relevant case, and if the relevant case is very standardized, better for me. And that we have done through our no arbitrage principle, through the Martingale representation theorem, and also the requirement that we want to make the process a martingale. We have already seen for the discrete situation that creating those martingales are possible. You can suitably choose the market probability so that returns become martingales. And now we have this martingale being equivalent to the Ito process representation, admitting an Ito process representation. So that's where we are now. But let me begin with the population growth model. This is also an example of that class. So we can start out by assuming that this deterministic part is a constant, because that is not our main point of interest. What we are really interested in is to tackle the stochastic part. So our representation here would be dnt dt as r plus alpha wt nt, or I can rewrite it as dnt equal to, or it is easier to think of this as the logarithmic form dnt by nt as rdt plus alpha dbt. So this is the canonical Ito process type of representation. But if you want to write it in terms of dnt, then basically you multiply by nt on both sides. So rnt dt and alpha nt dbt. Anyway, so that the basic equation that we are faced out with is this one, which is like, again, we have seen this on Monday. This will be like, again, the log normal distribution, because after taking log, it involves a normal distribution. So objective is to find this integral here, 0 to t dns by ns, and notionally it will be like rt plus alpha bt, because I can component wise integrate them, assuming b0 to be 0. So this is the notional integral version of the population growth model. Now I want to find the explicit distribution. So I want to evaluate the left hand side here, exactly how it looks. So to evaluate that, I will use the Ito's formula, and here the choice for my function g is obvious. It will be log x, because I am looking at the typical log derivative. So gtx will be log x independent of t, and this is of course only defined for positive x, but that is not a problem here because we are looking at a population model. So population size can be safely assumed to be strictly positive. So yt is basically log of xt, dxt is like this, udt plus vdv. If that is so, then dyt will be 1 by xt dxt minus 1 by 2xt square dxt whole square. This is the usual differentiation adding on to the second extra term of dxt square. I don't have a dt term here directly because my yt is not dependent on t explicitly here. So that is by dyt. That's the first step. which means d of log nt, because yt is log nt. So d log nt is 1 by nt dnt and 1 by 2nt square dnt whole square. And then I will replace the dnt by the equation that I have up here. This is my dnt. So that is straightforward. So dnt square I can evaluate. Again, most of the terms will be 0, all the dt dt and dt dbt terms, and only the dbt square term will survive. So dnt whole square is nothing but alpha square nt square dt. That's the first term, that's easy. So d log nt then becomes dnt by nt, and this term where this dnt square I have replaced by alpha square nt square dt. Simplifying, it becomes dnt by nt minus alpha square by 2 dt. So it becomes very, very simple because the nt square cancels out. So if I now integrate both sides, here I will get integral of dns by ns 0 to t. Right hand side, it will be log of nt by n naught. N naught comes because of the 0 time on the left hand limit, and this term will contribute half alpha square t.
Sir, should not that be minus half alpha square?
Exactly, I think so. So it must be minus half alpha square t. That is true. Yeah, because I have my own notes here, which I did not scan. So that is that. Okay, this is minus half alpha square t, of course. And then, because I not notionally already have seen that this must be equal to RT plus alpha BT, so I can equate it with that. Where am I? Equate it with that and say that this expression must be equal to RT plus alpha BT. So this was the original notional integral, and this is the explicit integral. Remember, this is minus, so that part has to be carefully taken.
So the plus is correct, right?
Um,
Because in the previous line we
that's
have
what
written
I'm thinking.
the
Because
alpha square by 2 would go to the other side because we are replacing dnt by nt as d of log nt nt plus alpha square dt.
oh,
Yeah, plus is correct.
but this one should be a minus. This one, the first one.
No, it should be I think what is written is correct, because what
What?
we are doing is in the previous line we have d of log nt is equal to dnt by nt minus alpha square dt. Then we are replacing dnt by nt by this form of the expression.
Uh-huh.
So alpha square dt goes to the other side as plus.
Yeah.
And then we have d
So,
of
which step are we talking about?
ওই আলফা স্কোয়ার বাই 2 টা বাদিকে নিয়ে নিন
d of log nt by nt plus alpha square dt টা হচ্ছে কি dnt by nt.
Yeah.
বাদিকে
This
alpha
one
square dt
will
টা নিয়ে
go.
গেলে
এটা প্লাসটা ঠিকই আছে
প্লাসটা ঠিকই আছে।
ওই আপনি আলফা স্কোয়ার বাই 2 টাকে বাদিকে নিয়ে যান, তাহলে কি হচ্ছে dnt বাই nt
এই
ইকুয়াল
expression
টু d of ln nt প্লাস আলফা স্কোয়ার বাই 2।
Okay.
এবার ইন্টিগ্রেশন
Right.
তাহলে হয়ে যাবে।
Okay. So before I do the integration, okay. I'm sorry. I got confused because. Okay, so now I understand. So in my notes, dnt by nt is written on one side, and this is already changed sides. Okay, so basically, whoever took this notes skipped one step, and that got me confused. So what I should have written here is dnt by nt equal to d log nt plus half alpha squared dt, right?
Yes sir.
Yeah, that's what I should have written, and then everything would have been right. So that step has been skipped, but I have it here in written in my notes. So next time I will scan my notes and upload. I don't do it because my handwriting is terrible. So, but it is creating additional trouble. All right, so back up. So d log nt is this one, dnt by nt minus half alpha square dt. I change sides, take dnt by nt on one side, and then do the integral. So here I do have plus half alpha square t. So far, so good. And this I equate with my notional solution up here. That is my notional solution, RT plus alpha BT. So I should have this equality as written here, that log nt by n naught plus half alpha square t equals RT plus alpha BT. And from that notional equality, now I will try to solve the nt completely, which I can do fairly easily, because this implies that nt must be n naught e to the power alpha bt plus r minus alpha square by 2 times t. Okay, so this is just changing sides and taking the anti-log, reversing the log. So the NT process is now, NT, remember it's a process, it is random, is now n naught, and the randomness comes from here, e to the power alpha bt. The remaining part is like a trend part. And this trend part you can easily recognize. This trend part is like the log normal distribution. So that part is what we would expect if there were no uncertainty in the differential equation, in the growth rate. Then we would not have alpha, and it would have been very nice, clear log normal distribution. Because we have randomness, we do have an additional term alpha bt. So now we have to find out the mean variance of these two things, because after all, we have a Gaussian process. So the first two moments will give us everything we want to know. First, expectation of nt. Expectation of nt will be n naught. This part is deterministic, it can come out. This part is the stochastic part, and we have to find the expectation. Expectation of e to the power alpha bt. Okay. So I want to evaluate this thing. So again, I take recourse to Ito's formula. So I want to get a differential equation for this part. So now that I have e to the power alpha bt, my choice for g will be e to the power alpha x. Again, typical choice. So I want to find this expectation, which is e to the power alpha bt dB. And my choice of x process here is simply bt, so that u is 0, v is 1. So I have x equal to bt, and gx is e to the power alpha bt. So g is e to the power alpha bt. I use Ito's formula. Derivatives are easily calculated, exponential function. So what do I have is d of y, d of gt bt, which is e to the power alpha bt, will look like this. So again, please check if this is correct. And I will also do that, if the derivative is correct. So these signs seems to, these signs are matching with whatever I wrote. So I hope they are correct. Is it okay? Just check with Ito's formula and verify. I can make mistakes, and anyway, sometimes mistakes are made just in writing. So is this correct from Ito's formula? Can one of you check and confirm?
ঠিকই তো আছে।
Okay. Okay, that's good to know. Okay, so if this is D, then again notionally I do the integration on both sides. The initial value is B0, which I can take to be 0. So I will have this integral dB of e to the power alpha bt, and again second integral for this part. So what I do have is expectation of e to the power alpha bt, which is the stochastic part here, given by 1 plus half alpha square 0 to t, again expectation of e to the power alpha bsds. Why is that? Because the integrand here inside works out to be the same. And this is not unexpected because we are working with exponential function. So the exponential function retains the same form under differentiation or integration. Just check that this is indeed how it is, that the expectation can be again written in terms of an integral over the expectation up to time s. And that actually solves our problem. Why? Because then I can just take this expectation as a function of time, because expectation is deterministic, and then solve the differential equation. Then it becomes actually a differential equation. So what I have here is ddt of the expectation is same as half alpha square expectation. Solving, we have the expectation of e to the power alpha bt as e to the power half alpha square t, and from initial conditions I can eliminate this constant of integration, because I have these conditions here that b0 was 0, and yeah, that is enough. So e to the power expectation of e to the power, yes, yes.
Oh,
Is it an attempted question or is it background noise? Yeah, I think it's background noise. Okay, so let me continue then. So then I just solve this differential equation, easy differential equation, and I have the final form for the expectation of e to the power alpha bt, which is e to the power half alpha square t. So I can then plug back into the NT process, because in the NT process that was the only stochastic part. Where is it? Yeah. So in expected NT, the remaining part was deterministic anyway. I only needed to evaluate this expectation, which we have done. So I plug them back, and then expected NT will be of this form, and not this e to the power r minus half alpha square t as before, and the expectation of the stochastic part is e to the power half alpha square t. And now you see the beauty of it. This alpha part term cancels out, and we are left with n naught e to the power rt. So what do we see here? What we see here is basically that the expectation is same as the stochastic path. I'm sorry, expectation is same as the deterministic path. Because if I did not have any stochastic component, if I did not have an alpha in the original formulation up here, then NT would have been exactly n naught e to the power rt. It is just an exponential growth model, and you know what it is. When I add the stochastic part, because it's a BT kind of stochastic part, so it's like a random noise with zero mean centered. So I will typically expect that the mean path will be same as before. The mean path will be same as the deterministic counterpart of the growth process. And in this case, it is indeed true. And this we see easily that expected NT is actually N naught e to the power RT, which would have been the solution in the deterministic case. Is that clear?
So had we taken expectation directly in the first differential equation we used, we would have arrived at the same result. So
Yes, of course. You are talking about this term here, correct?
no, I'm talking about the first differential equation from which the derivation began.
Which one?
It's before, even before that.
Even before that?
Yeah,
This is when
dnt
we
equal
start.
to alpha and right. This one, this is what I'm talking about.
Yes.
So if we take expectation here directly, then shouldn't it be? Oh no, okay. No, never mind.
No, okay. It is good to ask questions, and questions actually clarify matters, even if I am not answering them.
So I mean, what I was trying to say is that with respect to like dnt equal to r plus alpha wt and nt. So if we take expectation and then the expectation of wt goes to 0, and the wt is realized at the point t, and the nt part has already been done up to time t, so they are independent. So then that term goes down to 0. So expectation of dnt is just r into expectation of nt. So from that we can just directly say that
From that,
expectation.
you can also argue that the expectation will be same as the deterministic path. That's
Right,
what you are saying.
right.
Yes, you can. You can, but what you have just said is basically the same kind of logic, same kind of argument that we do for the martingale property of the Brownian motion.
Yeah.
So you will have to write a little bit, but yes, that's an alternative. We have done this more mechanically, more in a high school way, not only to waste time, but also to highlight the next part. You see, we need two moments. To understand the property of my NT process, I need two moments because of the normal distribution. Expectation idea, you are absolutely right. We could have done it from the first principle, from the definition. But this differential equation kind of formulation actually helps us to also look at the higher order moments. And I need one higher order moment because I need the variance of NT. So that's why these mechanical steps are useful, at least in this case. So the variance is, of course, ENT square minus E square NT, which I know exactly how to evaluate now because I have all the moments in my control at this point. So I will finally get the variance expression after some of these simplifications, and the result, of course, you should be able to write down if you remember the log normal distribution, which we necessarily don't, but the expressions are the same as you had in the log normal distribution. So the variance will be n naught square e to the power 2 RT e to the power alpha square t minus 1. How many of you actually remember the log normal distribution variance? Not that it's necessary, but do you?
I don't remember, at least.
Even I don't remember.
So most of you will definitely remember normal distribution, binomial
The
distribution.
only thing, the things about log normal distribution that I know
Yes.
is that log x follows normal, then x is the log normal, and its moment generating function derivatives.
So that is sufficient. That is absolutely sufficient. So you really don't need to know the expressions. Well, I did not ask you to, check whether you remember things, because remembering is not necessarily necessary. I just said because of curiosity, because I remember when we were doing economic statistics, at that point our professor was Professor Nikhilesh Bhattacharya. He has passed away a few years back. So Professor Nikhilesh Bhattacharya was a wizard in sampling schemes and sample survey techniques. So he did a lot of work for the National Sample Survey, and in particular, he did a lot of work on inequality and poverty calculations for India. And log normal distribution is a very useful toolbox for measuring income distributions. So at that point in the early days, log normal was a common candidate to fit income distributions. And that's why we were hammered with log normal distribution several times in class, again several times in assignments, and eventually we sort of memorized everything about log normal distribution. But well, that is not necessary anymore. But yes,
Sir,
yes.
instead of using log normal distribution, why don't we just take log transform and work with normal distribution itself?
Yes, yes, that's how you fit the data. When you are fitting the data, you just take log income and then fit normal distribution. But you see, when you are looking at the Gini coefficient and the Lorenz curve for the income, and if you have fitted the log normal distribution, the Gini coefficient and the Lorenz curve also has a parametric form which is related to these distributions moments. So those expressions were what we actually had to look at many times. You see, you have to remember that this was before computer period. Okay, so we had very rudimentary computers. So we did a lot of calculations by hand using calculators. And that's why explicit algebraic calculations were very important, because the more you simplify, the less you will have to calculate with the calculator. So that's why simple models were more popular than log normal distribution, and you can express the Gini coefficient in terms of the moments of that and so on. They were still ugly expressions, but at least you have a closed form expression. But well, I am not asking you to do any of that, but it is just trying to reminisce, because somehow whenever we look at a log normal distribution or a geometric Brownian motion, somehow I remember Professor Nikhilesh Bhattacharya. All right, so coming back to the real world. So we have looked at the population growth model, the generic version of the population growth model, which was our very first example. And we have gone through all the operational mechanical steps to solve for the process NT first, and then also the first two moments of that process. Because we are working with normal distribution, the first two moments are enough. So we have explicitly calculated the expectation and the variance function for NT. And this is our simplest canonical equation. You can see that you cannot make it any simpler. In general, your formulation would be in this class. For our purpose, all calculations will be in this etho class. And in the etho class, there is no guarantee that B or sigma will be constants, or it could be even worse. B sigma can explicitly depend on xt, and B, have their own stochastic nature. So that if you recall the Black-Scholes formulation that we did so far for the European call option, B and sigma were both taken as constants. B was just the market rate of interest, and sigma was considered to be independent of time, a constant sigma. For that situation, we will have a similar solution as this population growth model. And we did that. We have seen the Black-Scholes formula. A little bit of manipulation, but notionally it's straightforward. But most of the derivative contracts that we use in the market and that we have discussed earlier in that presentation will have both B and sigma varying with time, and also possibly stochastic. So solving those kind of differential equations will take more care, because then you'll have to look at possibly conditioning them, and for conditioning FT adaptedness will come in very useful. So that can be handled, but what will become more complicated is how to find these expectation variance kind of expressions. Very often there won't be closed form solutions. We will have some implicit equation or some approximation and then take it forward numerically. That is usually how this thing works. So before we close this solution discussion, let us just look at these final expressions here, and we can do some quick interpretations. So we have this NT process. So let me once again show you the NT process. The NT process is here, and I have this R minus half alpha square T as the trend part. So this trend part plays an important role, of course. You see, if my R is greater than half alpha square, remember alpha is like the volatility. So if R is more than half alpha square, I know that NT will grow without bounds. So as we look at a long enough period, T is going to infinity, NT will also go to infinity. And in the same manner, if R is less, then I know that NT will eventually go to 0 because the growth rate is negative. So these two are easy cases where population is exploding or imploding. The marginal case where R equals half alpha square, that is a very interesting case in itself, where there is no trend. If you look at NT again, there is no deterministic trend. This term will drop out. So it's a purely stochastic growth process here. So what we will see is NT will fluctuate, but the fluctuation will be between arbitrarily large and small values. So on the log scale, it will be arbitrarily positive or negative, because as you look at longer and longer interval of time, the variance is increasing. The variance is additive. So it will become arbitrarily fluctuating, but centered around the same value N naught. So a typical population growth model usually has a mixture of these properties. The models are not as simple as this. So you have models which usually reduces the growth rate after a certain level so that the population does not go to infinity and so on. And for epidemic models, we often try to create a situation where the population will actually implode. So if you are looking at the current COVID growth models, you will see some of these features. So this is not related to our finance course, but somehow this is very relevant at this particular point of time, because I know that some of you are interested and working on data and models related to the pandemic. Okay. So are there questions? Are there any questions? Okay, so if there are no questions, what I will do is I will stop here today, but I will leave you with something to read up. In the next class, by the way, the next class will be Monday evening, which will be a special lecture by Dr. Partha Chakraborty that you already know. So Monday morning, there will be no class. Wednesday, I will take the usual class. So on Wednesday, what I will do is I will look at the standard first order and second order stochastic differential equations. In your class 12, you have learned first order and second order differential equations, how to solve them, standard techniques. We will extend those techniques to the stochastic situation in the next class. So The material I'll be covering is from Whale Portstone, Introduction to Stochastic Process. I hope you are all now familiar with that book. It is also part of my syllabus, the prescribed textbooks in my syllabus. And the chapter that I am asking you to look at is chapter 6. Chapter 6 is on solving stochastic differential equations. Particularly, we are going to talk about the first order and the second order. And you will see that the technique of solving them are exactly similar to the deterministic case, with the expected additions to take care of the stochastic part. So we start out with the same technique as the deterministic case, usual integrating factor for the first order, the characteristic equation or that quadratic equation that we solve for the second order. Same techniques are still relevant here. And then we have to add on, because we have to also understand the stochastic nature of the solution. So I want you to look those up, because that material is absolutely familiar to you without the stochastic part, but the remaining thing. And if you just take a look at this chapter, next day the discussion will be very easy to do, because most of it is again mechanical application of certain formula and doing some manipulations to arrive at explicit solutions for some standard stochastic differential equation. Okay, so I will stop here.
Sir,
Yes.
so in the assignment, you have given a comment that it's very good but too long. So the word limit was 2000 to 3000 words, and my assignment was approximately 2800 words. So
Then
it's within that.
then I will edit my comment.
No, sir. I thought you'd cut my marks for.
No, I did not.
Yeah,
I did not.
yeah, okay.
I did not cut your marks. I could not count the words in the PDF file. So
Yeah.
just the length gave me the impression that it might be too long. I made the same comment for a few others also, I think.
লেন্থের জন্য নম্বর কাটলে আমার আর পেতে হতো না নম্বর।
Have you checked all the assignments?
No, not yet. Not yet. So I'm checking them in the classroom and posting the marks. So the ones I have checked, do you already see the marks?
No, sir.
No, sir.
No, sir.
No. So I think what I need to do is, you can see the comments I have made, correct?
Yeah.
Yes, sir.
So after I finish checking all of them, which should be sometime today, I think I will have to send an email to all of you, so that each one of you now then get to see the marks. Because now the marks are showing as draft. I am also doing it for the first time, and I am very bad with softwares. So all I can see is when I am posting the marks, they are now written as draft. So probably I have to click somewhere to finalize, and then you will be informed about the marks.
Okay, sir.
And then if I get stuck, I will basically ask one of you to help me out, which is likely.
Sir,
Yes.
sir, regarding the next assignment, does it has to be from finance, or it can be anything from statistics, the research papers?
What is the name of this course?
No, that's why I just asked. Like, it has to be directly from something from finance, or maybe related to something.
No, maybe he's asking,
That's right.
can we like select papers that try to predict financial models using statistics, or that kind of paper, or it has to be on financial modeling?
Yeah, that was my.
Okay. No. I am not strictly keeping it only to math finance. You can have statistics papers, you can have economics papers, as long as they are modeling some financial situation.
Sir, after the verification,
I have already approved a couple of papers. I think Shweta sent one and Shubhrojyoti sent another, which are more on the statistical side. That is okay, because the main question is finance. And I think DSR showed me a paper which is a very macroeconomics kind of thing, but that was also okay, because it is a financial some of the financial factors in the market that are being analyzed. So I am flexible, but yes, it has to be in the context of finance. I don't mind whether it is maths
Okay, sir.
or economics or statistics or even computer science. There are a lot of people who are doing very good work in finance who are from the computer science background. So even those papers are okay, but you have to show me and I must be convinced about the technical quality of the paper.
Okay, sir.
Yeah. And I have already posted a comment in my classroom that I still think a few of you have not submitted. Rahul is here. Rahul, have you submitted the assignment?
No, sir. Actually, I didn't submit. I will submit soon.
Yeah, so there are a few more people who have not submitted, and now the penalty is on, but you still need to submit, otherwise it will be 0. So try to submit as soon as possible and just tell the others, because I know that many of those who have not submitted are not here, so it is no point. But I have made that post, and once I have graded all the assignments, I will try to post all the marks. Hopefully Google will make it easy enough for me. Otherwise, I know some of you can help me. Okay,
Okay,
all
sir.
right. Any other questions?
Sir, when will we start group work? The another project kind of thing.
The third one will be group work.
Yeah. So what will be the group size?
I have not thought about it yet. Give me a few days.
Okay.
Are we at the liberty to choose our partners, or would you be assigning them?
Oh, you are of course at liberty to choose your partners, but that will depend on the group size, correct?
Yeah, it would be at least
Yeah.
2, right? Otherwise, it's not a group.
No. Of course, it will be at least 2. So, no,
Yeah.
but I have to look at the total number. If it is like a multiple of 3, then I'll make it 3. That is something I'm not sure of, that how many are finally in the credit and non-credit category.
And the non-credits also have to do everything.
Yes, because they have marks. There will be marks in their final marks.
Yes.
And
Non-credit বেশি নেই, যা আছে credit-ই বেশি।
initially Vaishnavi verified that data for me. Vaishnavi, do you remember?
Which one, sir?
The
Credit, non-credit. Yes, sir. That was verified by students.
yes, so I think there were 31 or 2 credit and 2 non-credit, something like that.
Yeah.
So that number I have to manage somehow. So I will tell you next week.
Okay, sir.
All right. So we will stop today. And Monday, the class is in the evening from 7 p.m. And that will be a special lecture, blockchain in finance.